word problems, everything should be constructed from scratch. So we have to introduce our own variables that make sense, and then use those variables to construct objective function, constraint inequalities, and then start to solve the problem. So there is just this preliminary work that has to be done before we can begin to solve the problem. And that preliminary work is all about organizing the information we are given in mathematical or symbolic terms. Because all the information is given to us in plain English form, we have to first convert that to mathematical form, symbolic form. And to do that, we're going to have to introduce variables. For most of you, this might be the last math course you're taking, but the importance of problems like this or sections like this is that you can apply the same approach to solving word problems in any context, whether you're taking a finance course, an accounting course, marketing, or any of the other major courses that you have to take. This approach to solving word problems is always the same. You'll have to introduce your own variables, then you establish a relationship between the variables that are not known and the variables that are known, and you solve the problem after that. So having said that, let's see how this works in practice using the geometric method. We're going to do two word problems, and this being the first one. Okay, so here's the full problem text. So this is all the information given to us in plain English, right? If you try to solve this problem right away, it's hopeless because there's too much information here that is thrown at us. We need to first organize this before we can talk about solving it. So let's do that. I'm going to begin from the beginning, from the start of the problem, and organize the information first. So I'm not solving anything. I'm just organizing all this information in symbolic form. So we have an appliance company that has a sale on microwaves and stoves, and each microwave requires 2 hours, a certain number of hours to unpack and set up, and each of the stoves requires 1 hour. So the storeroom space is limited. Right there, we have a clue that we have some information given to us about a constraint. In real-world business situation, I'm sure you all know, there are all kinds of constraints, right? Spatial constraints, budgetary constraints, time constraints. All of this, you have to look for those clues in these word problems, for optimization word problems. So that's one of them. The budget of the store, also another constraint, right? The budget of the store allows only for 80 hours of employee time for unpacking and setup. So we're just making mental note about what kind of information we have. And then microwaves sell for $300 each and stoves sell for $200 each. How many of each should the store order to maximize revenue? These two last words are extremely important because they're telling us what type of an objective function we are optimizing. It is a revenue function, right? So let's label it as that. So capital R to denote revenue. The other importance of this is that it tells us, if you look carefully, it tells us what variables we should use in this problem. Because if we look carefully from here, in this box, it says microwaves sell for $300 each and stoves sell for $200 each. So these two items, microwaves and stoves, are bringing in a revenue stream. So how many of each should the store order to maximize revenue? So the variables we need to use in this problem must be one for microwaves, number of microwaves, because they're saying how many of each, how many. One variable should denote the number of microwaves sold. The other variable we need is a variable to indicate the number of stoves sold. That's very important because once you establish the objective function, and if you look at your notes from, or if you look at the video from last time, the first item on the steps to the geometric approach was establish the objective function. This is where that is very helpful advice, because by establishing the objective function, you are doing something very important too, which is which variables should also be included as part of the constraint inequalities. You can't have two different or multiple different variables in the objective function and in the constraint inequalities. You can have more than one variable or two or more variables in the objective function, but these variables should be exactly the same ones you're using in the constraint inequalities. Okay, and with this, we are clear what we should use in the objective function. So let us label them, because this is a very important part of organizing the information. We have to introduce our own variables. So M, let's take that as the number of microwave ovens sold. And let's take S, capital S, as the number of stoves sold. Okay, so given these two variables, let's set up the objective function, which is the revenue function, because that's what we're maximizing. So we can write revenue equals, now each microwave is being sold for $300 each. So 300 M, right? If you tell me you sold 10 microwave ovens, then I know the revenue stream from selling microwaves was $3,000. So that's part of the revenue function. Plus the stoves are being sold for $200 each. So let me label these. So microwaves are being sold for $300 each, and the stoves for $200 each. So 200S. So that's our objective function. We're trying to maximize this objective function. So now, before we've even gotten to constraint inequalities, we know we should use M and S. No other variables are acceptable in the constraints. We must use the same variables in the constraints as we use in the objective function. So now let's read about the constraints that we had. And when we read it for the first time, some things popped up, right? It's the space is limited, the budget for the employee time was limited. We're going to make use of those. Okay, so each microwave requires 2 hours to unpack and set up. Okay, let's attach that information to this variable M that we introduced, right? So I'm going to put an arrow here, and I'm going to say 2, that's 2 hours for unpacking and setting up. Let me just use U, 2 hours to unpack and set up. And each stove, that's this variable, requires just 1 hour to unpack and set up, or 1 U. The U's are just acronyms for me to remember what that number refers to. So 2U refers to 2 hours of unpacking and setting up, and 1U represents 1 hour of unpacking and setup. Then we're going to read on. The storeroom space is limited to 50 items. Okay, so right from that statement, and the fact that we had M and S, we can write down a constraint for that. So space is limited to 50 items, right? So we can store up to 50 items there. So that's how I'm going to organize that information like that for now, and we're going to build on this. But let's read on. And the budget of the store allows only 8 hours of employee time for unpacking and setting up. So this piece about employee time is critical in terms of how much time is needed to put together a microwave and how much time is needed to put together a stove. So time, or employee time to be exact, is limited to or allows for only 80 hours. So up to 80 hours we have for employee time. Okay, so now let's use this information to set up our constraint inequalities. First of all, for space, that's the easy one, right? So we know that given this constraint, M the number of microwave ovens, plus S, which represents the number of stoves, should be less than or equal to 50, right? Remember what we labeled these variables as. So M plus S must be less than or equal to 50, because we don't have more space than 50 of these items in this store. So that's one of the constraint inequalities. Notice we're using the same variables we used in the objective function. So let's set up the other constraint inequality based on this information. So employee time cannot exceed 80 hours for unpacking and setting up. Okay, so we know that each microwave takes 2 hours to unpack and set up. So 2M plus each stove is taking 1 hour to unpack and set up. So 1S, or let me just say S, right? 1S is just S. S should not exceed 80 hours. So these are the two constraint inequalities. Compare these with the objective function, we have the same variables, right? Let's not forget that under no circumstance we can have a negative number of microwaves at the store or a negative number of stoves, right? So let's make that clear. So M should be greater than or equal to 0, and S should also be greater than or equal to 0. So if you look at what we've done up to this point, is just organizing the information we were given in plain English into symbolic form that makes sense in this context. Okay, so we're now ready to solve this problem using the geometric approach. Keep in mind, when you organize information symbolically, like we've done here, your aim should be to capture all that information that was given to you in plain text in such a way that if someone comes and rips the text away from you, rips this piece away from you, you're not going to miss it because you've captured all that information in this symbolic form. Okay, so now because we're using the geometric approach, we need to draw graphs of these constraint inequalities. Ahead of that, we have to establish from the outset what is going to be our x-axis, which variable is going to be our y-axis, because instead of x and y, we're using m and s. Okay, it doesn't make any difference which way we pick m and s to be on the axis. What's important is that you should make that determination now. So what I'm going to do is simply say, instead of x comma y, that is equal to m comma s, right? So our x-axis is going to be represented by the variable m, and our y-axis is going to be represented by the variable s. Knowing that, what we're going to do is graph each of these constraint inequalities. So these are our constraints, right? Those 4. We're going to graph these one by one, find the region of solution, find the feasible corner points, plug those corner points here, and determine where this revenue function is maximized. Okay, so that's basically the game plan. First, let's graph this one, m plus s less than or equal to 50. So we have m plus s equals 50, right? Because we're finding the boundary line first. So if m equals 0, I'm finding the intercepts as before, like the video lesson for section 4.2. Then s equals 50, and we decided that s is represented along the y-axis. So therefore, we have 0, 50, our y-intercept. Then, or next, if s equals 0, then m equals 50. Therefore, the x-intercept is going to be 50, comma 0. So let's graph this before we move to this second inequality. Because everything is going to be on the positive side, right? M and S have to be greater than or equal to 0. I'm going to dedicate all of this blank space to the positive side. Like that, and like this. So we decided that the M would be represented along the x-axis, and S would be represented along the y-axis. These numbers are not too, they are large, so I'm going to have to make my increments 10 wide. So this will be, I think this would be, if I go this much, it would be good. So 10, 20, 30, 40, 50, 60, 70, and 80. I want to do the same thing along the y-axis. So we have 10, 20, 30, 40, 50, 60, 70, and 80. And 80, right? Okay, so let's plot these 2 points. We have 0, comma 50, which is that. That's 0, comma 50. And then we have 50, comma 0. That would be here. 50, comma 0. So let's connect these with a solid line, right? Because solid line, because we had less than or equal to, and less than or equal to. So that's why. Like that. And I'm going to write on top of this what inequality it is associated with, which is m plus s less than or equal to 50. Okay, so remember that we have to, this is the boundary line. We're going to have to find which side of this line is the solution of this inequality. We can pick a test point. A useful test point, an easy one too, would be 0, comma 0, or the origin. So let's plug that into this inequality. So testing 0, comma 0, we're going to have 0 plus 0 less than or equal to 50, right? If we plug 0 here, we get that. Is that a true mathematical statement? Absolutely. 0 is less than or equal to 50. So the same side as our test point is the solution of this inequality. I'm going to lightly shade this like that with these arrows. So the same side as the test point, right? Because it checked out. If it didn't check out, if this test point didn't check out, I would shade the other side of that line. Okay, so let's graph the other inequality, which is this one, right? 2m plus s less than or equal to 80. So first, just like before, we're going to find the boundary line by finding the intercepts of this equality. Okay, so just like before, I'm going to use the intercepts. If m equals 0, then s equals 80. Therefore, we have 0, comma 80. as our y-intercept, and if s equals 0, then m equals 40, right? If you plug in for s with 0, and then you have 2m equals 80, and then 80 divided by 2 for m, we get 40, right? So the x-intercept is 40 comma 0. Let's plot these 2 points. 0 comma 80 would be way up here. 40 comma 0 would be here. And once again, we can connect these with a solid line. Like that. Here, I'm just going to write the inequality that is associated with this line right next to it. So 2m plus s less than or equal to 80, right? Okay, so now we have to pick a test point to see which side of that line is the solution. So testing 0 comma 0 again. We're going to have 0 plus 0 less than or equal to 80. If you plug in 0 there. Is this a correct mathematical statement? Absolutely. So it checked out. So the same side of this line as the test point is the solution of that inequality. Okay, so we also know that m and s have to be greater than or equal to 0. So we cannot go to the left of this line because that's when m would be negative. And we cannot dip below this line because that's when s would be negative. So our solution region is right there where we have overlap of individual solutions. And let me make the shading darker here. Right? That's the solution region. So now we need to identify all the corner points. So we already know 0 comma 0 is a corner point, but is it a feasible corner point? Would we have a business left if we stored 0 microwave and 0 stoves? No. So that one is not feasible. So we can toss that corner point out when we optimize our revenue function. So we are left with only 3 corner points, right? This one we already know, it's 0 comma 50. This one we know is 40 comma 0. But this one we don't know what the coordinates are, right? So we have to find that. Let's find that corner points by setting up a system. Because that point is the intersection of this line, 2m plus s less than or equal to 80, and that line, which is m plus s less than or equal to 50. So let's set that up. M plus s equals 50, because we were looking for that point, the coordinates of that point. And then 2m plus s equals 80. Okay. So let's multiply either equation by a number that would help us eliminate one of these variables and then solve for the other and plug back and solve for the variable that was eliminated. So I'm going to multiply the top equation by -1, and that's going to give me minus m minus s. I'm distributing, right, to both sides, minus 50. You're going to distribute this to 50 as well. And then 2m plus s equals 80. So let's add these 2 equations together. The s's drop out as we intended. The m's, 2m minus m is just m, equals 80 minus 50 is 30, right? So we found m. Now let's plug this into either one and solve for s. So we have I'm going to use the first equation because it's easier. So using m plus s equals 50, we have 30 plus s equals 50, so s equals 20. So we have s, we have m, we have the coordinates of that point then figured out. So we have 30 comma 20 as the coordinates of that point. Great. So now we have the coordinates of all 3 points. We're going to maximize this objective function. So let me write it down. R equals 300m plus 200s. We're maximizing this using those 3 points. This time I'm going to go clockwise. So at 0, 50, then at 30, comma 20, at 40, comma 0. All right, I grabbed each of those points. Let me move this up like that. We won't need the graph at this point. We have everything we need right here. Okay, so R would be equal to 300 times 0 plus 200 times 50. And that's going to give us $10,000 of revenue. So R equals, with this setup, we have 300 times 30 plus 200 times 20. So we have 9,000 plus 4,000. We have 13,000 here of revenue. And finally, 300 times 40 plus 200 times 0. And we have $12,000 of revenue there. So it's clear that our revenue is maximized when the store or the appliance store has 30 microwaves and 20 stoves. Okay, so we can write that conclusion. So that's basically clear right there. But we can add that the revenue is maximum or maximized at $13,000 when 30 microwaves and 20 stoves are stored and sold. Okay, so with a question like this, you might be asked, okay, set up what is the objective function, right? You have the word problem. The question says, read the problem, write down the objective function. That's one question I can ask you about this. Or I might ask, what are the constraint inequalities? So you should give me the constraint inequalities. And you write those down. Or I might ask, what is the maximum revenue? Or at which point, how many microwaves and how many stoves would the store need to have or sell in order to maximize revenue? So all of those are questions that I can ask from on a problem like this. Okay, so let's move to another example. Because this next one is the second example. Once I finish writing the entire problem, it's a good idea if you pause the video, solve it on your own as best as you can, and then come back to the video to see how I set up the solution. See, these clues, I hope you're getting used to seeing these, picking up these clues. At most, these are usually clues for a constraint inequality. There's another at most phrase, right? Very important. Okay, so this is our full description of the problem here. And so if we read from the beginning, just to get a feel for what kind of information, what kind of a problem this is. So a factory manufactures 2 products, okay, each requiring the use of 3 machines. That gives us plenty of things to think about. The first machine can be used at most 70 hours, so that's a constraint. The second machine at most 40 hours, that's another constraint. And the third machine at most 90 hours. So we have 3 minimum constraints just by reading the problem. It's telling us that we have at least 3 constraints. The first product requires 2 hours on machine 1, 1 hour on machine 2, and 1 hour on machine 3. The second product requires 1 hour on each machines 1 and 2, and 3 hours on machine 3. If the profit is $35 per unit for the first product and $65 per unit for the second product, how many units of each product should be manufactured to maximize profit? This last part of this problem, this is so important because it tells us what the objective function is, which is a profit function, and it also tells us what variables we should have in the objective function and the constraint inequalities, because these are each products, and we have two products, right? So let's introduce our variables in a way that is helpful in this context. We know we're looking for the number of two products, so let's introduce variables like that. So I'm going to call P1 as the number of product 1 items manufactured. I'm just going to shorten that because I'm running out of space there. Right? That's P1. So this is the step you have to do for all kinds of word problems in any class. You have to introduce variables first. Then P2, number of product 2, or the second product, items manufactured. Now that we have these variables, let's construct our objective function. Let's do that because it's going to tell us which variables we have to have in the rest of the problem, right? So the profit is $35 per unit for the first product and $65 per unit for the second product. So we can easily use that information to set up the profit function. P would be equal to 35 times P1 plus 65 times P2. This is our objective function. This is the function that we are going to have to maximize. So we now know that the constraint inequalities should have these two variables in them, P1 and P2. All right, so let's read the problem from the beginning and attach information to the variables we introduced. That's how we organize the information. So let me just write here, organize information. Very, very important to solving any word problem. So it says that the first machine, we have three machines, right? Machine 1, 2, and 3. So let me give those variables M1, M2, and M3. Remember, we're organizing the information. I'm not going to use M1, M2, M3 in my constraints, but I'm using these letters and variables to organize my information. So the first machine can be used at most 70 hours. So this machine is at most 70, so less than or equal to 70. The second machine, it says the second machine at most 40 hours, okay? So M2 less than or equal to 40. And the third machine at most 90 hours. Well, M3 less than or equal to 90. Okay, then it says the first product, that's P1, requires 2 hours on machine 1. Let's attach that information to our variable. So 2 M1, right? 2 hours on M1. The first product requires 2 hours on machine 1, 1 hour on machine 2, and 1 hour on machine 3. So 1 hour on machine 2 and 1 hour on machine 3. Right? Notice what is happening. We find out what variables we need to introduce. then attach information to those variables. Then we are told that the second product, this one, the second product, requires 1 hour each on machines 1 and 2 and 3 hours on machine 3. Okay, so let's attach information to this as well. 1 hour on machine 1, 1 hour on machine 2, and 3 hours on machine 3. Okay, so that's how we organize the information. Now somebody can take all of this text away from me and I won't miss it because I've organized all of that information. All right, great. So let's write down our constraint inequalities. We have 3 constraints, right? The constraint on each machine. So the constraint on machine 1, constraint on machine 2, and constraint on machine 3. All right. So we can write that on machine 1 cannot be used more than 70 hours, right? Less than or equal to 70 hours. We know that. So 2 hours is spent on each product 1 on machine 1. So we say, I'm looking at that, 2P1 plus product 2, 1 hour is spent on machine 1, right? So 1 times P2 is just P2. So 2P1 plus P2 has to be less than or equal to 70. Now let's move to the constraint on machine 2. Machine 2 cannot be used more than 40 hours. So we have 1 hour of machine product 1 has to take 1 hour on machine 2. So P1, 1 times P1 is just P1. And then 1 hour of the product 2 takes 1 hour on machine 2 as well. So P1 plus P2 less than or equal to 40. M3, product 1 takes 1 hour on machine 3, so that's 1 times P1 is P1. And then product 2 takes 3 hours on machine 3, so plus 3 P2, and that should not exceed 90 hours. And remember, we at no point we can have negative number of products produced, right? So P1 is greater than or equal to 0, P2 is greater than or equal to 0. So we have everything we need to solve this problem using the geometric approach. We have our objective function, our variables, and then the constraint inequalities. So let's do that. We're going to graph each of these boundary lines, find the solution, find the corner points, and plug in. Okay, I'm going to pick up a little bit speed here to get this done before my time runs out on today's recording. All right, first let's find this line, 2P1 plus P2 equals 70. So if P1 equals 0, then P2 equals 70. By the way, let's take x to P1 to be x and P2 to be y, which means x comma y should be equal to P1 comma P2. So P1 is going to be on the x-axis. And then, so based on this, then we have 0 comma 70 as the y-intercept. If P2 equals 0, then P1 would be equal to 35, right? 70 divided by 2. So we have 35 comma 0 as that, as the x-intercept. So everything is going to be on the positive side of the axis. So I'm going to draw my graph so that most of or all of this blank space is dedicated to the positive side. Like that and like this. So this is P1 and that's P2. The increment, these numbers are large, so I'm going to give these increments of 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90. The same here. 10, 20, 30, 40, 50, 60, 70. I need only up to 70 along the P2 axis. So 0, 70 is this point, 35, is here, 35 is somewhere between 30 and 40. So let's connect these with a solid line. Right, like this. So this is 2P1 plus P2 less than or equal to 70. Now pick a test point, testing 0, 0. If you plug that in this inequality, you get 0 plus 0 less than or equal to 70, which is correct. So this side, or the same side as the test point, which is 0, 0, is the solution, right? Okay, so let's plot the other line, or the other constraint, which was P1 plus P2 equals 40. Okay, so if P1 equals 0, then P2 equals 40. So we have 0, 40. If P2 equals 0, then P1 equals 40. So we have 40, 0 as the x-intercept. So let's plot these. We have 0, 40 and 40, 0. Let's connect those with a straight line, a straight solid line, right? And I'm going to write this next to this, write the inequality next to the line, so I don't lose track of which line is associated with which inequality. Once again, we can pick a test point, right? And the test point can be the origin again, because this line does not go through the origin. So testing 0, 0, we have 0 plus 0 less than or equal to 40, which is a true statement. So the same side as the test point is the solution of that inequality. Okay, we have one more inequality to plot, and that is P1 plus 3 P2 equals 90. Equals 90. So if P1 equals 0, then we have 3P2 equals 90. So P2 equals 90 divided by 3, 30, or 0, 30. If P2 equals 0, then P1 equals 90. So we have 90, 0 as the x-intercept. Let's plot these 2 points, 0, 30 and 90, 0. 0, 30 would be here. 90, 0 would be here. Let's connect those with a straight line. a test point tells us that the bottom side of that line is the solution. So this is P1 plus 3P2 less than or equal to 90. So we know that testing 0, comma 0, that'll be 0 plus 0 less than or equal to 90. That checks out if you plug that into this. So we have the bottom side of this line as the solution. So the solution region or the overlapping region, and we know everything has to be positive, right? Because we can't have negative number of products. The solution region is right there. And I'm going to darken this region. Okay, so clearly this one, this corner point is not feasible, right? If the manufacturer produces 0 product 1 and 0 product 2, they're not going to stay in business. So we have 1, 2, 3, 4 corner points to consider. This one we already know. That's 0, comma 30. We know this one as well. This one is 0, comma 40. That one is 0, comma 40. Or sorry, 0, comma 35 actually. 0, comma 35. Sorry, 35, comma 0 is that point. And then these 2 points we don't know. These two. We have to figure them out. So that point, this one, is the intersection of 2 lines, P1 plus P2 equals 40, and the other line, which is P1 plus 3P2 equals 90. That's one of the systems we need to solve. The other system we need to solve would be the system of this line, again P1 plus P2 equals 40, intersection of that line with this one, 2P1 plus P2 equals 70. So you can see that system is one we need to solve, and this system is another system we need to solve. And we should be able to maximize this. So if using the methods we've talked about so far, right? So I want to make sure that you fully followed why we have these systems. So that point is the intersection of those 2 lines. P1, that's one of the lines. You can see it on this screen. And this line, which is P1 plus 3P2 equals 90. This point is the intersection of this line, which is again P1 plus P2 equals 40. Let me move it up so you can see it. P1 plus P2 equals 40. That's that line. And this line, which has this equation, 2P1 plus P2 equals 70. So those are the 2 systems. Because I'm a little bit short on time, let me skip this part where you have to solve the system and find P1 and P2, right? You should know how to solve this. If you don't, please ask about it on the discussion board. But when you solve this, you'll get 15, comma 25. So when you solve this system, you get this point for that. And so this is that. And the other point, that one, when you solve this system for that, you would get 30, comma 10. right? Solve these systems, see if you get those values. 15 comma 25 up here, and then 30 comma 10 for this system. Now we have all the coordinates for all the feasible corner points, right? So we can easily answer that question for the objective function. So the objective function was profit equals 35 P1 plus 65 P2, and the feasible corner points are as follows. These are the feasible ones, right? So we toss out 0, 0, 35, 0, and 30, 10, 15, 25. These are the 2 points that we solve for using those two systems. And finally, 0, 30. Okay, so plugging in, and this is P1, P2, right? So P is equal to 35 times 35 plus 65 times 0, and we get $1,225 of profit from that corner. And then P equals 35 times 30 plus 65 times 10, and we get $1,700 from that, of profit from that. And then P equals 35 times 15 plus 65 times 25, and we get $2,150 of profit from that. And finally, P equals 35 times 0 plus 65 times 30, and we get $1,950 of profit from that. So basically, we have the maximum profit happening at this point. Maximum profit is $2,150, and it will happen when we have 15 units of the first product and 25 units of the second product manufactured. So max profit is $2,150 when we have 15 of the product 1 and 25 of the product 2. So these word problems, as I said earlier, they are always solved the same way. It doesn't matter what course you're taking. So you're going to have to introduce variables. So you read the problem carefully and introduce your own variables that make sense. In this case, we picked P1 and P2 because we were talking about how many of one product and a second product we need to manufacture to maximize and sell and to maximize profit. And then establish a relationship between the variables that are known and the variables that you're looking for, and then solve the problem using the appropriate formula for that context. If it's a finance problem, if it's an accounting or economics or a physics or chemistry problem, you use the appropriate formula for that. But the approach is always the same. Okay, I hope this helped you become familiar with solving word problems using the geometric approach, at least, if not become more comfortable with solving word problems in general. So with that, we have wrapped up section 4.3. And please, if you have any trouble finding these points, solving the system and finding these points, please post your questions on the discussion board. All right. Good of you to persist through this video, and I look forward to see you all again for the next lesson, which will be sections 5.1 and 5.2 together. For now, stay safe and have a nice day.